Good morning. This is the series of your ultrasonic testing, conventional ultrasonic testing. We will try to cover all the ultrasonic testing inspection aspects in four part. Part A that we will deal today, and in this part A, we'll try to learn the basic physics of conventional ultrasonic inspection using in the industry. First of all, if you want to know what is ultrasonic inspection and what is ultrasound, simply we know that ultrasonic inspection is a volumetric non-destructive testing to identify the defect or discontinuity in your inspection part which are associated into your volume. Nowadays, ultrasonic inspection is a most popular volumetric inspection, and in some areas it has replaced the most popular radiographic inspection. Due to the hazards of radiation and availability of the time period for conduct the radiography, particularly night time, then in place of that, ultrasonic inspection is hazardless and it can be carried out anywhere in any place, and the results of the inspection instantaneously you can read out and the reporting can be done. So that is the basic benefit of ultrasonic inspections. And nowadays in industry, ultrasound is much more popular because in compared to the conventional ultrasonic inspection, a lot of advanced ultrasonic technology like that phased array, time of flight diffraction, and full matrix capture is there. But all the advanced ultrasonic inspection is stand on the point of your conventional ultrasonic. That means if you have a good idea regarding the conventional ultrasonic testing and its physics, it will be better for you to understand the advanced technique. So simply we can say what is the ultrasound means what is the sound. Sound is a kind of energy which is produced from some vibrational body, and when the sound is produced from some vibrational body, it will travel into the forward directions in the form of wave. And when it will be travel into the forward directions, that is in a medium, it will propagating into the medium by forming a sine wave. And in the sine wave, it will its x-axis that will be indicate the traveling path, and y-axis that will indicate the amplitude. So each and every time, the nature of the wave indicates that its amplitude, which is denoted into the y-axis, that will be going to be increases to the top, and then it will come to the null point, and the same thing will be reversed into the opposite direction. So during this propagation, one complete cycle of that particular wave, that is known as the frequency of sound, and the unit of frequency is denoted by hertz. So one cycles is equivalent to 1 hertz, and during the one cycle, whatever the distance traveled by the sound, that is known as the wavelength of the sound. So if the number of cycle is multiplied with the wavelength, that will give you the distance traveled by sound in unique time interval, and that is the velocity. So the relations of the velocity with the frequency and wavelength is v, that is denoted by velocity, is equal to frequency into wavelength. So when we are talking about the frequency, that has a unit of hertz. That means 1 cycles per second, that will be considered as a 1 hertz. But in industrial applications, we have the requirement for the penetration in your inspection parts. In that scenario, multiple hertz of frequencies required. So if 1000 hertz we are considering, it will be known as 1 kilohertz, and 10,000 cycles per second, yeah, 10,000 hertz, that will be known as a 1 megahertz. So 1 megahertz is the 10 to the power 6 hertz, and 1 kilohertz, that is the 10 to the power 3 hertz. So depending upon the frequency of the sound has been divided into the three categories, that is subsonic, sonic, and ultrasonic. If the frequency of the sound is more than 20 kilohertz, then it will be known as a ultrasonic range, and that frequency range we are using for the industrial application. We know that each and every NDT method has a specific sensitivity requirement is there. If your method is not sensitive enough, such that we cannot able to identify the finer defects. So in ultrasonic, sensitivity of ultrasonic inspections is clearly depends upon the lambda value, and it is denoted by lambda by. That is half of the wavelength that will be equivalent to the minimum defect size that can be identified into the ultrasonic testing. Now the lambda is has a relationship with the frequency of the sound. If we are considering velocity of sound of a particular medium in standard temperature and pressure, it's constant. So if V is constant, so frequency and wavelength has a relations of inversely proportional. So if the wavelength will be increases, frequency will be decreases. So with the increase of frequency, wavelength will decrease, and in the lower frequency, wavelength will be high. So we need the lower wavelength. That means we need the higher frequency. So high frequency sound has a much more sensitive to detect the finer defect in ultrasonic inspection. When the ultrasound is propagating into our forward medium, the propagation is occurred into the four-way. One is known as compressional, a longitudinal wave mode propagation. Second is shear, a transverse wave mode propagation. Third one is the surface wave propagation, and fourth one is known as lamp, a plate wave propagation. When the sound is traveling into the forward medium in the form of longitudinal wave, the directions of propagation of sound and the directions of the collisions or the particle movement will be parallel to each other. If it is transverse in wave propagation mode, in that scenario, the directions of propagation of sound and the particle movement of the medium will be perpendicular to each other. And due to the opposite direction movement of the particle, definitely shear wave velocity of sound in a particular medium will be half of its longitudinal wave velocity. So when in a same medium, when sound is traveling throughout the longitudinal wave, whatever the velocity it is, if it is traveled in the same medium as a transverse wave, it will be half of the longitudinal wave velocity. Third one, that is known as the surface wave, and in this scenario, in generally the name implies that the wave is propagating throughout the surface of the inspection part, and it can penetrate up to the one wavelength depth of your inspection part. In this scenario, the particle movement of the inspection medium will be approximately elliptical in nature, and the velocity of the surface wave will be approximately 8 to 10% of the shear wave velocity. Due to the lower velocity, surface wave can be damped by a very heavy grease or the weighty finger, and follows the curves and reflected by the sharp corner for the determinations of surface crack. So for the identification of surface crack, we are using surface wave. And the fourth wave propagation mode, that is known as lamp, a plate wave propagation, and it is produced by the manipulations of the surface waves and other used mainly to test the very thin material or plates And the velocity of the lamp and plate wave propagation mode will be vary depending upon the plate thickness and its frequency. There are two type of particle movement is possible into the lamp and plate wave. One is the symmetrical and another is the asymmetrical. So in a same medium, uh, if the sound wave propagation mode has changed, there will be the changes into the velocity. For example, when the sound is traveling into the air, its velocity is 330 meter per second. When it is traveling to the water, it will be 1480 meter per second. When the sound is traveling throughout the still in the form of longitudinal wave, the velocity will be 5920 meter per second. And if the in the same material that is in still, the sound is traveling throughout the transverse wave, it will be 3250 meter per second. So velocity of the sound mainly depends upon the density and elastic modulus of your inspection pattern. Uh, when the sound is traveling from the one medium to another medium, like that of the light waves, it will follow the same principles. That means something percentage of the sound will be transmitted into the second medium and something percentage will be reflected into the first medium also. The how much percentage of sound and how much percentage of uh, sound will be reflected and transmitted, that depends upon the one values, one I can say it's characters of that particular type of medium that is known as acoustical impedance. And the meaning of the acoustical impedance is it is the multiplications of the density of that particular medium and the velocity of sound in that particular medium. So the acoustical impedance that is denoted by Z, that is rho into V. That means density into velocity. So if we are considering that sound is traveling from one medium to another medium and both the medium has the acoustical impedance value of Z1 and Z2. So due to the difference in their acoustical impedance value, something percentage of sound will be transmitted and something percentage will be reflected back. So how much percentage will be reflected and how much percentage will be transmitted, that we can be calculated by using the formula here. Reflection R is equal to Z2 minus Z1 whole square by Z2 plus Z1 whole square, and transmission, that is 4Z1 Z2 by Z1 plus Z2 whole square. For example, here, suppose the sound is traveling from the still to water. Still has the acoustical impedance value of 46.7 into 10 to the power 6, and water has the acoustical impedance value of 1.48 into 10 to the power 6. By using the above formula, we can calculate percentage of reflection, and here the percentage of reflection is 88.09%. That means if the sound is traveling from the still to water, Z1 to Z2, then water to still, in that scenario, 88.09% sound will be reflected into the medium 1 and approximately 12% will be transmitted into the medium 2. For examples, air has a very less acoustical impedance value compared to the still. So when the sound will be traveling from air to still, 99% sound will be reflected back into the air and only 1% will be transmitted to the still. So when we are going to inspect the still component, we need the sound need to be travel into the still surface in a very high percentage of transmission, but by the air, it is not possible because air is a bad transmitter of ultrasound. So during the ultrasonic inspection, we need to be expel the air from our inspection surface and in between the searching unit or the probe, and the air need to be expelled by replacing a proper couplant. And the meaning of the couplant means the couplant is a specific type of a liquid or something medium which has a acoustical impedance values which is in between that of the workpiece and the piezoelectric crystal containing into the ultrasound producing probes. So some kind of materials like that of some wetting agents or glycerins or some thick oil like that of motor oil or grease we are introduced in between the probe and the workpiece such that the maximum amount of sound can be transmitted into our inspection. When the sound is traveling from one medium to another medium and the angle of incident is 0 degree, then there will be no chances for the conversations of the mode. That means if the sound is traveling from medium 1 and the incident angle is 0 degree and the nature of the wave is longitudinal wave. So when the sound will be travel into the second medium, it will be the same, that is the longitudinal. There will be no changes into the mode conversation will be there. But if there is an incident angle and the sound is traveling from one medium to another medium with a definite incident angle, like say theta 1, which is not 0 degree, other than 0 degree, then there will be a mode conversion into the medium 2 and something percentage of the incident longitudinal will be converted to the longitudinal wave in medium 2 and some percentage will be converted to the shear wave also. But when the sound will be travel into the medium 2, it will create the another angle and that angle is known as the angle of refraction. Snell's law states that the angular relationship between the incident and reflected angle with respect to their sine value with that is the ratio of these two is equal to their velocity ratio. So sine theta 1 here divided by velocity of longitudinal wave in medium 1 is equal to sine theta 2, where theta 2 is the refracted angle into the medium 2 divided by velocity of sound into the medium. So according to the Snell's law, if for a particular incident angle and the first longitudinal wave, say longitudinal wave is traveling from medium 1 to medium 2 in a definite incident angle, what will happen? It will be converted to the two modes, something percentage into longitudinal and something percentage into the shear. Longitudinal wave has a higher velocity, so the angle of refraction of longitudinal wave will be higher compared to the shear wave. But if we are going to increase the incident angle, then in a particular incident angle, the longitudinal wave into the medium 2 that has a refracted angle of 90 degree, and in that scenario the incident angle is known as the first critical angle. If we are going to increase the incident angle furthermore in such a way that the refracted angle of shear wave will be reached to 90 degree, and in that scenario no wave will be exist into the medium. So if we want to create the shear wave into the second medium for our angular inspection purposes, in that scenario, incident angle of the longitudinal wave, which is coming from the first medium, that will be more than first critical angle and less than second critical angle. Here, this is the examples of calculation where we are considering the prospects to still considering their velocities of 5960 meter per second and the velocity of 3250 meter per second for the shear wave, and the velocity of prospects is 2730 meter per second. Then the first and second critical angle for still it will be approximately 27 and 54 degrees. So if we want to create the angle, that means shear wave into the medium 2, the incident angle shall be more than first critical angle but less than second critical angle. So for our ultrasonic inspection purposes, we need some instruments that is known as the search units or probe. And that search unit or probe are producing the desired frequency ultrasound, and that unique frequency, resonant frequent probes we are using for our inspection purposes. There are three type of probe we are using in conventional ultrasonic. One is the straight beam probe. Second is the TR probe, and third is the angle beam probe. The straight beam and TR probe both are producing the longitudinal wave, and angle beam probe produce the shear wave in a particular or definite angle. So normal beam and TR beam, a normal probe and angle probe, these are the single piezoelectric crystals probes, but the TR probe, which is known as the transmitter receiver probe, is a twin crystals probe. That means in a same probe housing, two crystals are there. One is acting as a transmitter and another is acting as a receiver. TR probe in generally we are using for the lower thickness, and normal probe into the higher thickness due to the uh, what we can say dead zone issues. And angle beam we are using for the determinations of defects which are oriented in a particular plane. Each and every probe has the dead zones, and that dead zones is due to the uh, whatever the moment of inertia of the internal crystal present into the crystal. When the electrical pulse will be impinged into the piezoelectric crystals, it will vibrate it up to the certain time period. And during this vibration, when it will produce the low energetic ultrasound that can able to penetrate up to the certain distance from the near surface. And if any defect is associated into the near surface of your inspection part, then that scattered echo and the reflections from the defect echo and in the lower thickness, initial and backward echo, both will become very continuously or simultaneously, and the resolutions to determine this near surface defect will be very, very less. So that means the near surface resolution, particularly in case of single crystal probe and normally normal probe, it's very difficult to identify the near surface defect because near surface resolution is less in case of normal probe. That is known as dead zone for the normal probe. The basic principles of ultrasonic inspection is we know that in ultrasonic inspection we are using a searching element or probe that contain a piezoelectric crystal. It is when connected with the ultrasonic machines, electrical energy is generally transmitted to the piezoelectric crystal. It will vibrate to its resonant frequency, and the ultrasound will be produced, and that sound will be propagated into the inspection medium. When the sound will be traveling through the medium, whatever the acoustical barrier is there, the sound will be reflected back, and that reflected reflected sound energy will be returned back to the same crystal that will act as a receiver, and the received ultrasonic energy will be transferred to the ultrasonic machine as a electrical signal, and we are getting the echo. So first echo we will be getting from the initial pulse, as the initial pulse from the front wall of the object, and then if any discontinuity is not there, then it will be the back wall, and the back wall echo will be repeated. But suppose if any discontinuity is there in our inspection part, then the sound will be not able to travel throughout the back wall, and it will be returned back from the defects, and in between the initial echo and back wall echo there is a possibility of formations of defects echo, and by this way in actual depth we can identify what is the indication any kind of discontinuity is present in your inspection part or not. There are a lot of advantages into the ultrasonic inspection. It is very, very sensitive for both the surface and subsurface discontinuity. Depth of penetration for the flaw detections or measurement is superior to the other NDT method. Only single side is excess for the pulse echo type of technique. Lot of technique is there. We will be elaborately discussed in our next session. It is highly accurate to determine the reflector position and estimation of size and shape. Minimal part preparation is required. Electronic equipment we are using so that it provides the instantaneous results. Detailed imaging can be produced into the automated and in advanced technology. It has other uses such as the thickness measurements in addition to the flaw detections. There are some limitations also there into the ultrasonic inspection surface that must be accessible for the transmit by ultrasound. Skill and training is much more extensive than other NDT method. It normally require a coupling medium to promote the transfer of sound energy into the test specimen. Material which are very, very rough in surface, irregular in shape, and very, very small and exceptionally thin are not homogeneous. That's a difficult inspect. Cast iron and other coarse grained material are difficult to inspect due to the lower sound transmission and high signal to noise ratio. Linear defect oriented parallel to the sound stream may go undetected, and reference standards are required for both the equipment and calibration and the characterizations of flaws. So each and every step when we will carry out the ultrasonic inspection, we need some reference block or reference reflector from where we will take the reference. So that's the basics of your ultrasonic inspections. That means the basic principle of ultrasonic inspection is acoustical barrier mismatch. So due to the acoustical impedance variation into the interface of these two material, something percentage will be reflected back, and that reflected energy will be converted to the electrical signal in the form of echo into the CRT, that means in the ultrasonic machine screen, and we can analyze according to their positions and the nature of echo. So that's all about the first part. We will soon meet in our part B. In there, we will be discussing regarding the type of probes, its character, and the beam profile which we are using for our inspection purposes. Thank you.